This video introduces the notion of an op-amp, or operational amplifier. It corresponds to section 19.1 of the Applied Analog Electronics textbook. What is an op-amp? An op-amp is a standard building block that we use for building a lot of different circuits. And it is a differential amplifier. So we have an amplifier with two inputs, a positive one and a negative one, and a single output. Now, unlike the instrumentation amplifier we talked about before, there is no separate reference voltage input. The output here is referenced to a point halfway between the power supplies. So we have two power supplies, and for the designs that we do in this class, we nearly always connect the negative power supply to ground so that we have a single-sided supply. So this might be something like 3.3 volts here. That's different from what most electronics books do in introducing op-amps. Most of them will use symmetric power supplies where we would have a positive voltage and a negative voltage so that our midway reference voltage is 0 volts. That makes the math a little easier, but power supplies are expensive compared to other forms of electronics. So modern design quite often forgoes having a symmetric power supply. Okay, so what do we do with this amplifier? What is it that it does? Well, we'll talk in the next few videos about what we use op-amps for, but let's go through a little bit what it does. All right. The output here depends on, of course, these two inputs. And because this is a differential amplifier, it really only depends on the difference between them. And we want to multiply that difference by some gain. We'll call that gain A. And we'll say V out is equal to that. Well, except for that we needed this reference to something. So this is V out minus V mid, where V mid is halfway between those two power supplies. And I'd like to just be able to close the parenthesis here, but there's one little thing here, and that is that it's sometimes not perfect, and there's a little offset voltage you would have to add on here. And so this offset voltage ideally is 0. In practice, it's in a small range around 0. A here, well, in the ideal op-amp, it's infinite. We can't achieve that either. So in practice, we get values like A might be about 500,000, and we might have V offset is less than maybe 4 millivolts. And of course, these specs do matter on an op-amp, and you can find them on data sheets. Though the open loop gain, which is what this gain is called, is often specified in decibels because it's a large number. And so by taking the logarithm of it, you get a smaller number that's easier to work with. Let's take a look at what we expect this thing to do. Well, if we plot VPA minus VMA on the x-axis and V out on the y-axis, what we expect as VP minus VA goes more and more negative, that this thing will go towards the bottom rail, and then this thing will shoot up with a very high slope and hit this top rail. So this would be like 3.3 volts here, because that's what the power supply was. Not all op-amps will go rail to rail like this, from 0 volts to 3.3 volts. The ones we happen to use in this class are rail-to-rail ones. Sometimes they'll have a narrower range, so you have to pay attention to that when you're specifying an op-amp too, is what's the output range. The slope here in the middle, part where we actually use the op-amp, that is a slope of A. So that's where we get the gain. And let's take a look at this thing sort of zooming in at that very, very vertical line, because the slope of 500,000 basically looks like a straight vertical line, unless you scale things. Okay, so here I've done it where if you look on the bottom axis, we've got 250 microvolts plus or minus 10 microvolts here. So this is a very narrow range, around 250 microvolts, and we're going from 0 to 3.3 in just this 20 microvolt range. And this is fairly typical of an op-amp. With the 250 microvolt offset that we have there, that's not unusual. It could have been minus 250. It might even vary a little bit depending on the temperature of the device. So this is not something that's you have a lot of control over, that offset. But it generally stays pretty much the same for your circuit, though it changes from part to part. So it's not a time varying thing, it's just a component, maybe temperature varying thing. But we use this thing usually only in that middle part there where this is approximated well by a straight line, because we want the amplifier to be linear. So what you've got is a pretty narrow range that the inputs can be. They cannot be very far apart. Now there are versions that look a lot like an op-amp that have a similar sort of characteristic here. They're called comparators. We will look at those quite a bit later in the course. The main difference between an op-amp and a comparator is that the comparator is intended to be used with the output either high or low. It's not intended to be used in this linear region in the middle. And so it's been optimized to get very fast transitions between those two extreme points. The op-amps are designed to be used in this range in the middle, and various trade-offs are made in order to achieve good linearity there. And in fact, what I've shown here with a very smooth rounded corners here is not really very desirable for an op-amp, and so you might want to have something that looks more like, over that same range around, you might want to have something that looks much more like a straight line over the entire range and putting up with sharp corners when it clips. And that then would give you a wider range over which you can use the amplifier, because it stays straight for a wider input range. Okay, so basic features I've talked about: the op-amp here, the open loop gain, and the voltage offset. And those are the things we need to worry about most when we're working with low frequency signals. When we're working with high frequency signals, we'll have to look at the gain bandwidth product, and we'll talk about that more in later videos.